All right, welcome everybody to our seventh installment in this series in this lecture series on computer game AI. And if you remember, the last couple of lectures we had deeper looks into how to realize programs that could play a deterministic, turn-based, two-player, zero-sum games of perfect information. And if you remember, that basically boils down to thinking about trees. Trees are, of course, a staple in computer science, a very beautiful data structure, lots of algorithms known for how to process trees, how to compute with trees. And indeed, this is what we are going to do today. We'll take a step back from what we have done so far and look at the idea of tree search from a more general perspective. Right? And by stepping back, that will allow us next time to dive in even deeper. Right, so let's first look at what we did last time, then we'll look at tree search algorithms from a more general point of view, and then we'll conclude with a summary. Yeah, so far, as I already said, we looked into deterministic turn-based two-player zero-sum games of perfect information. And we studied the problem of computing strategies for these kind of games. That is the problem of coming up with a series of moves that would lead the player who is to move to a goal state, which we said basically is a state in which the player who is to move will win whatever game we're talking about. And when thinking about how to compute these strategies, series of auspicious moves, we saw that we may represent the course of these kind of games, two-player turn-based games, in terms of game trees, where every node in the tree represents a state within the game, some situation that occurred from a series of moves so far. And well, again, the problem was to look for a winning state or a plan that would lead us to a winning state. We saw that we could do that using tree search algorithms. In particular, we looked at these classical ideas of min-max searches, maybe in combination with alpha-beta pruning, stuff like that. And we also looked, that was last time, at the idea of depth-restricted searches, where we saw that we typically are facing the problem of having to expand these game trees down to the very last level of the tree. It could be very expensive in terms of computation and maybe even in terms of memory. Very expensive idea, works beautifully, but hardly feasible in practice. So an idea could be to cut off the search after a couple of steps of look ahead. And we saw that if we were to do that, we of course do not have access to the information in the leaf nodes anymore, so we need some function that would allow us to evaluate whatever state we cut the search off. And yeah, these functions are also called heuristics, and last time I referred to them as eval of n, where n is a placeholder for the game state we are interested in evaluating. And then there was a blunder on my slides, and I have to correct this today. One of the things I explained to you was that there are many different ways as to how we could compute these evaluation functions, and then basically, as to this date, still require a lot of human ingenuity, a lot of human intervention. It's very difficult to come up with these functions, although it can be done, but typically they are not learned from many plays or gameplays, but rather designed by the human programmers. Well, one idea was, or like a general idea was, to compute features for every game state. Right? Many different kinds of features are possible. We had a look at an example in the case of tic-tac-toe, where we actually computed two features. the number of possible winning lines for the one player and the number of possible winning lines for the others, and then we combined them in a linear combination, basically subtracted them. That's one way of computing such an evaluation function. More general idea could be to compute a lot of such features, a lot of numbers, and to collect these numbers in a vector. Let's call it feature vector f, and the subscript indicates the node n for which we do compute these features. Now then, if we agree that that is possible, that however we do it, but we can compute features and collect them in vectors, we can then resort to techniques from the realm of pattern recognition and machine learning. In particular, what we can do is, for instance, have the computer play many games, and maybe actually, progress these games down to the bottom level of the game tree, collect many feature vectors for all the different states we encounter in these in this offline phase, and then to cluster them. Right, and we'll look into the idea of clustering in much more detail later on. But basically, we could say that if we are given a lot of feature vectors for many different game states, we can cluster them, which would provide us with, say, categories or clusters. Let's call them C. And in particular, once we have determined clusters of feature vectors, of game states, we can then, of course, assign an arbitrary game state n, which we encounter during our exploration of the game tree while playing a game, to one of the clusters we have determined previously. Right? And then if in addition, during this offline phase where the program has learned about the game and its possible sequences of moves and what kind of moves lead to winning states and losing states, we can create statistics about how often one of these categories encountered at some higher level in the tree will lead to a win later on in the game, how often this category will lead to a losing situation, and how often it will lead to a draw. And that allows us to define probabilities. It's just relative frequencies, relative number of wins, relative number of losses, relative number of draws. And here was the confusion last time. So let us denote these probabilities. Say the probability of winning for category Cn. This is the parentheses were set horribly wrong last time, but now it's correct. So somehow we could determine these cluster-specific probabilities. Right? Now, if we have them, we can, of course, say multiply the probability of winning for this cluster with a value of +1, which would sort of indicate the utility or payoff for a winning state. If we have the probability of losing, we may multiply it by -1, which -1 would indicate the payoff of a losing game state, terminal state. Yeah, and if we multiply something by 0, the result is always 0, so whatever. But if you look at this, this is an expected value. Right? We have a variable that can assume values of +1, -1, and 0. That variable is denoting the outcome of the game. And we have, weights, which sum to 1, they are probabilities. So indeed what we do compute here is a so-called expected value. This is great because this expression allows us to compute an expected value for the likely outcome of a game where we are in a state n that belongs to a certain cluster C. And if we choose this variable that denotes the final outcome of the game as +, -1, and 0, then of course this expected value will be a number between -1 and +1. But it might be indeed actually +1. if, for instance, this probability of losing was 0 and the probability of generating a draw was 0, then of course, because of this constraint, the probability of winning in this cluster is 1, but 1 times plus 1 is 1. Same holds for situations where a loss is certain, and so on and so forth. But this expected value will always be a number between -1 and +1, and of course, the higher that number is, the better for us to sort of continue exploring that game state. Because that would indicate that on average, the current state we are in usually leads to a win. Okay, so now this is correct, and actually on the slides for the last lectures, I have corrected the placement of the parentheses. So if you have a look at the slides on the site online, then this is correct. Now, as I said already, today we will take a step back. We'll look at this from a much more general perspective. In particular, we will see that this idea of tree searching is a fairly general concept. And the point I'm trying to hit home today is that it does not only apply to deterministic, turn-based, two-player, zero-sum games of perfect information, but indeed to any kind of state space that is discrete and that has a partial ordering relation, however we define that, because if it has a pattern, then we can come up with a tree. In particular, we can apply the idea of tree searching to any kind of problem with a discrete state space where we have to find a path from an initial state to a goal state. Okay? And well, in a nutshell, what I'm trying to hit home today is that tree search algorithms can be used whenever the state space can be modeled as a graph. And these game trees are, of course, very specific graphs. Every tree is a graph, so yeah, it worked beautifully there. Now, here is a motivating example. A couple of years ago, I was invited to the University of Bremen, actually to give a talk on game AI, funnily enough. And of course, I'm living in the city of Bonn, and being invited to Bremen posed me with the problem of finding a way as how to get to Bremen. And well, here are a couple of German cities in northwestern Germany, and there you see a part of the railroad network of Deutsche Bahn, the German railroad operator. So my problem was to plan an efficient, that's cost efficient and time efficient, trip from Bonn to Bremen. So what could I do? Now, obvious idea is to charter a helicopter and fly. Right? That will be a very time efficient way of getting from Bonn to Bremen, but this is hardly cost efficient. It's beyond what I can afford. But this would be one possible plan for reaching my destination in Bremen. That was too expensive for me, so my idea was to focus on riding the train. And there you have different options. For instance, one way of reaching Bremen from Bonn would be to choose these high-speed trains, the ICEs, which unfortunately go via Hanover, Hamburg, and then to Bremen. So this is a good idea. It is something that is considerably fast, reasonably fast. Yeah, it is much cheaper than chartering a helicopter. But yeah, we look at that. I don't like these deviations. Why should I go to Hamburg first if I actually want to go to Bremen? So a third option was, again, to travel by train, but not solely relying on these high-speed trains. And it turns out there was another path which led me over Münster, Osnabrück, and then to Bremen. And that was indeed the option I choose in the end. Right, choose in the end. So, how could we? Yeah.
Why didn't you choose the path between Bonn and Hannover with ICE and?
Oh, there was like with the time constraints, I would have had to wait a long time in Hanover, whatever. So that was not a perfect option. Yeah, of course. Yeah, maybe that would have been a fourth option, but that turned out to be the one that was sort of giving a good trade-off between time and cost efficiency. How could we come up with these kind of solutions automatically? That is the problem we are going to study in the next couple of lectures. And in order to do so, we first have to familiarize ourselves again with a lot of terms and definitions. A lot of terminology I will use frequently, and I'll have to introduce it so that you know what I am talking about when I'm talking about these things. First of all, let's look into the notion of a well-defined problem. A well-defined problem consists of the following components. So this is a notion in this area of AI and planning, and I say something is a well-defined problem if there is an initial state, and note that this node in the graph has switched its color from black to red. That is the node representing the city of Bonn. And the initial state is a state an agent, in that case me, starts in. It of course could be a game state, empty tic-tac-toe board, whatever. We have an initial state. We also have a successor function, or have to have a successor function. And that is a function or a representation that describes possible actions or moves available to an agent in a certain state. We have seen these successor functions encoded in terms of game trees, and here of course the successor function would be traveling to this node, which indicates the city of Cologne. It looks like probably in this example the only option we have when in state Bonn. The interesting thing is that if we have an initial state and a successor function, that, given the initial state, tells us about the possible subsequent states, and then for every subsequent state tells us about the possible subsequent states, and so on and so forth. Then indeed these two ingredients define the state space. Remember tic-tac-toe or chess. We sort of start on a either empty board or a board with the pieces arranged in the initial position, and then the rules of the game, whatever game we are playing, define possible moves. If we carry out one of these moves, we end up in another game state. Being in that game state, there might be other possible moves. If we carry out one of these moves, we end up in another game state. If we were to carry out all possible moves, we could, just by having information about the initial state and possible successors, in terms of actions available to us, come up with a whole state space. Right? And now that we sort of already have agreed on the notion of initial state and successor function, which describes actions possible to us that lead us to another state, we can already mention the idea of a path, which is nothing but a sequence of states connected by moves. And again, if our problem domain can be modeled as a graph, then basically every state is a node in the graph, and every move is an edge in the graph. And so like the edges indicate what possible choices we have to transit to another state. And in that sense, a path in such a graph is just a sequence of nodes connected by edges. There definitely has to be a goal test function. Right? Eventually we have to decide if by looking at possible successor states we would actually end up in the goal state or in a goal situation. For this problem of traveling to Bremen from Bonn, the goal state obviously is the city of Bremen, represented by this node now colored in green. And I don't know, if we traverse this graph, maybe we're lucky and eventually end up in this node that represents Bremen, then we know we could terminate our search. So we have to have a criterion that would tell us when to stop searching. And finally, ideally, I said the problem is to come up with a sort of cost-efficient path, cost-efficient sequences of moves. We need to have a way of evaluating what it costs us to carry out a certain move. And that is, we need to have a function that assigns numeric costs to path. And the obvious, easiest way of doing it is to actually define step costs. And that would mean, in this example, to assign a number to every edge. And if we choose to move along an edge, we would have to, in a sense, pay the costs assigned to that edge. And then the cost of a path would be nothing other than the sum of all these step costs. That is obvious. Yeah?
Now, I have a question. Your local task, is the cost of the path, is the actual time you are spending to travel from city to city, or the time that train spends on it and plus the time you wait?
So he has asked about how to define, I paraphrase it, these costs, right? And that depends on what you want to optimize. So I said my problem was to come up with a cost and time efficient plan for how to travel from Bonn to Bremen. And so I would have to have a step cost function that combines measurements of time spent traveling along that edge and measurements of costs I have to pay to Deutsche Bahn, to carry me along that edge with a specific mode of transportation chosen. Of course, I could, again, come up with very sophisticated cost functions that would consider many different aspects as to what I want to optimize. Like, for instance, waiting time could also be an aspect that could be included in a cost function. I'm not actually talking about how to define these. Right? That is, again, something human engineers have to scratch their heads about.
So we are considering just general problem.
Very general problem. We're master program at the university. We don't care about these nasty details. In general, there will be costs associated with all the edges. We don't care about the nature of these costs. All we care about is that they are numbers. That somehow there is a function that takes lots of different things and does some crunching and returns a number, and that number is assigned to these edges. Okay. That's it. If we have these four ingredients, we are dealing with a so-called well-defined problem. Then what is the solution? Obviously, a solution in this formulation of problem solving is a path from the goal state to the initial state to the goal state. But there are, as we see, many possible paths. So the question is, like, if there are many solutions, then what is the one we should go for? And the so-called optimal solution would then be a solution of minimum path costs. Right? This is a very short path, but it's a very expensive one because the helicopter is expensive. This is a somewhat extended path, which is possibly rather fast in terms of travel time, but maybe rather costly in terms of paying for the trains that have to be taken there. And this is a reasonably short path, which, reasonably short traveling time and also reasonably low costs having to be paid to the carrier. So there are these cost functions which we really don't know how to specifically define them. We have to decide that situation dependent, problem dependent. But if we have them, we could cast every problem, or like these problems that have to do with discrete state spaces, in terms of searching problems where we search for paths of minimum cost. And that is the general idea here. The general idea is that this problem of planning, or the problem of problem solving, can be dealt with in terms of the expansion of search trees. Right? And we've seen a lot of examples in the last couple of lectures, but again, today we are taking a step back and assume a more general perspective. If we agree that we carry out tree searches, then what we do is that, again, we start in some initial state, which I'll call n not now. We explore the state space. And that's, we generate successor states and examine their merits and recursively progress through the state space. We start in some state, we generate possible successors, somehow we, say, evaluate them, and then for the best evaluated node, we continue recursively in the hope that eventually we will reach a or the goal state. Right? In game playing, it does not really matter which winning state we reach. We just want to reach one winning state. In planning travel trips, it is actually indeed just a single state we want to reach and not a choice of state. Again, these details are problem dependent. Okay, we thus have to come up with a search strategy. I already said, we expand possible successors and evaluate them. What does that mean? Right, we have to think about how to evaluate them or how to expand successors of successors. And whatever option we choose there defines our search strategy. So the term search strategy in this context is just referring to an algorithm for how to choose successor states which we want to examine further. And here is, already on this slide, another important notion. It's the notion of the fringe. And the fringe is the set of nodes. And again, I'm using the term node and state interchangeably. Right? We're talking about basically states we are in and looking for successor states, but they are nodes in graphs or trees, so states are nodes. The fringe refers to the set of nodes which, during our search for an optimal solution, a path from the initial state to some goal, have been generated but not examined further yet. And in a slight abuse of terminology, I'll refer to every node in the fringe as a leaf. Typically, a leaf of a tree is a node without successors, but we'll see in examples later on that nodes in the fringe, as we have already generated but not fully examined yet, they may have certain successors, but they are still fringe nodes because we have not looked at all of their successors yet. And there is where I'm violating the usual terminology. Right? Usually a leaf is a node without successors. Every node in the fringe from now on is also a leaf, even though it may have successors. Here is the very general idea as to how we can do these kind of attack these kind of problem-solving problems. How to search for solutions. This function is called tree search. Well, there is a problem and a strategy. And a fringe, and I'm using this sort of Pythonic notation to indicate that when we start with this function, the fringe contains a single node, and that is the initial state. Okay? Now, the idea is to do the following. While there is something to be explored in the fringe, we then choose one of the elements of the fringe to expand it further, to continue our search from there. this is where we need a strategy, right? Therefore, the problem and strategy are both like very abstract parameters of this function. Now, say we have chosen a node from the fringe, we would carry out our goal test. Is that node the or one of the possible goal states? If so, then we're done. We have solved our problem. We have somehow reached the goal state. We could sort of pass back the information as to how we reached it back to the function and call this one. So we can return the solution. If the node we have chosen from the fringe is not the goal state, we will remove it from the fringe and extend the fringe by the set of the successors of the node n we just chose. And then we will call this function recursively with the newly declared or defined fringe. That's it. Yeah.
When did they add n to fringe?
Pardon?
Have they ever added n to fringe?
We start with one single element in the fringe,
Yeah.
right? Then we select an element out of the fringe. So if we start this function, we select the initial node, right? We remove the initial node from the fringe and add all its successors to the fringe. So once again, his question was like, how do we actually modify the fringe? Here, we always start with a fringe set of just one node that is the initial node, the state we are starting in. Now, when we first enter this function, the fringe therefore is not empty, and we can choose a leaf that is one node out of the fringe. But if we first enter this function, there is just one node in the fringe, right? So, and this is not the goal state. Typically could be, but then that would be a very silly problem. So when we start this procedure, there is just one node in the fringe. We select that one, because it's the only one we can, and we remove it from the fringe, but we extend the fringe by all the successors of that node. Now, if that initial state has like 15 successors, all of a sudden, the fringe will contain 15 nodes.
Okay, but we say nodes out of fringe are called leaf nodes.
Yeah.
But, and we say that choose a leaf
Yeah.
n for expansion. This means that n is not from fringe.
It means n is from fringe. Every node in the fringe is called a leaf, and we choose. Yes, this is what I spent 2 minutes justifying my violation of the usual terminology. Every node in the fringe is a leaf, even though it has successors.
Then it's fine.
Yeah. This is I shouldn't do it, but I'm doing it anyway. Yeah.
Just to clear, so it's a DepthFirst search, right?
We don't know that yet. Very good question. So his question was, is this a DepthFirst search? It depends on that word strategy. Right? We will see that this still allows for anything. We have not specified whether or not this is a DepthFirst search. However, again, when the fringe is not empty, we select a node from the fringe. At the beginning, there's just one node in there, so we can't actually choose. We have to pick that one. We remove it from the fringe. We extend the fringe by all the successors of this node and call this thing recursively. So what may happen is that we terminate this while loop because the fringe somehow is empty, but we have not found a solution. So if we ever reach this point here without leaving the function there, we know there is something wrong, utterly wrong, and I'm just including that here. All right, what is a problem with this silly algorithm?
Kind of brute force. No?
Oh yeah, it's very brute force. This will be the topic for today. This is all brute force. You're right, but there is another problem. This was too simple.
We can find a solution that's not optimal.
Oh yeah, that can happen. Yeah.
That's going to be the last solution that we find, we're not going to find.
Yeah. So she pointed out that using this we may find a solution that is not optimal. Indeed, that is a severe problem. something we will not worry about today, but yes. No, my problem is the following. So I start in Bonn. I want to travel to Bremen. So from here, Fringe node is like this is the only node in the Fringe. I selected, I extend the Fringe by the successors. There's just one successor. And now I am in this state. This thing actually has, in a sense, 3 successors. Right? Now, I have traveled from Bonn to Cologne. And if I'm stupid, I would explore, well, what would happen if I travel back to Bonn? This is something we shouldn't do. Right? So we need another ingredient in this tree search algorithm. And this is just to motivate the necessity of this additional ingredient, and that is the set of closed nodes.
But we were talking about tree, right? So, and when we are talking about successors in the tree.
Yeah, we're talking about very general graph search here, using trees, and by expanding nodes we create a tree. But with the algorithm we have seen here, there is nothing well successors. I should have called it neighbors. I guess this is I should have called it neighbors. In general, they are neighbors, and I should have called it neighbors.
So this is not a directed graph?
In general, it's not. If it was, that would great. It would be great. I have not. So her question was: is it a directed graph? And in general, it is not. If it was a directed graph, we would not run into the problem I just sketched. So, we start in a state, make a move, reach another state. There we have 3 possible moves. One of them could actually take us back to where we started, which would be a bad thing to do. And therefore, we should keep track of the states we already explored. And these states will be tracked in this list or set called closed. So from now on, we always have 2 sets. One is the Fringe, containing the states we want to explore or can explore next. And the other one is closed, set closed, which contains the nodes we have already explored. And therefore, so we do the same. If the Fringe is not empty, we select a node, we include this new node in the closed set, remove it from the Fringe, and extend the Fringe by all possible successors, or neighbors, I should say, of this current node, if they are not in the closed set. Now we're good. Right, with these 2 ingredients, we can now begin to worry about the term strategy. Yeah, why would we need strategies? Basically, we have to avoid infinite expansions. And introducing this idea of the closed set already is part of a strategy, if you wish, because it avoids some lethal way of expanding nodes forever and ever and ever and ever. But even with the closed set, depending on what problem we are dealing with, we can expand for quite a while until we finally reach a goal or the goal. And so therefore we want to avoid that and want to come up with ways that would allow us to quickly determine solutions, if any. What kind of search strategies could we think about? It's basically 2 very general ideas. The one is called uninformed search or blind search, and the other informed or heuristic search. In uninformed search, all we look at is the structure of the state space. There we basically are happy with the fact that there exists nodes and edges, which sort of like states and actions, and that in a certain state there is a set of actions leading to other states, from which there are other states, sets of actions leading to other states, and so on and so forth. This is all we care about there. And in this informed and heuristic approaches to problem solving, we may indeed consider additional knowledge, for instance, such as features of a state, features of a node. And maybe this additional knowledge, whatever, features, attributes, contextual knowledge, however it is available to us, maybe this additional knowledge actually helps us in our search. Uninformed and informed searches. And today we shall focus on uninformed searches, understand those, and then take it from there next time and the time after that. So, obviously, and I know you all have seen that in your bachelor studies, but let's look at DepthFirst Search. So we are starting in a certain initial state, it's called and not. You see that there is a tree below a not. Again, in this example, we do know the tree, but in general, of course, we don't. So we have to expand and not. And then from the nodes we find by expanding and not, we have to expand them further. So the tree typically comes into being while actually searching. In our examples, the trees are there and we sort of uncover them while searching. Right? So we expand the root in DepthFirst Search, and then its successors, and then their successors. And that is to say, this idea of DepthFirst Search, we expand the search tree level by level. And I'm already telling you, now the solution we are looking for in this contrived example is in this leaf node. So let's see how we would reach that leaf node by DepthFirst Search. First, we expand successor N1. Then we expand successor N2, then N3, and then N4. Now we have uncovered the first level of the tree. And now we expand all the successors of N1, then all the successors of N2, all the successors of N3, and all the successors of N4, which is just one node in this example. Okay, we have now looked at many possible states. None of these is our solution yet, or does indicate our solution yet. So we have to continue expanding nodes in this tree level by level. We reach the next level, expand N13, 14, 15, 16, then we are done. This is DepthFirst Search. Right? That is, we are given an initial state and a successor function. We apply that successor function to the initial state, and it yields all the successor states of the initial state. Once we have them, we iterate over the successor states and apply the successor function to each of them, giving us the successors of the successors. Right? Again, this is to say that we expand level L in the tree to its fullest before we consider level L plus 1. Yeah, some implementation tricks, neat ideas. If you ever are faced with the problem of having to implement this, and I hope you never will, because there should be libraries that do that for you, but if you ever had to, then note that here you could realize the fringe, which I have talked about as a set. Right? Mathematically, it is a set. Of course, when you're a computer scientist, we have to implement mathematical concepts on computers, and that is, we have to think about suitable data structures. And for DepthFirst Search, it turns out that a suitable data structure for the fringe is a FIFO queue, first in, first out. Here is how you could, if you would have to, do that in Python. So we are given a fringe, right? And in Python we assume this is just a list. And we have to select, according to our strategy, a node from the fringe. But we are doing DepthFirst Search, so we just look at the first element in the fringe. In Python, we can call the function pop. It's the function of this list. And that gives us the first element of the fringe and removes it from the fringe immediately. This is great, because this is what we want to have. And then we extend the fringe by appending the successors of the node we just sort of popped out of the fringe to the fringe. And since we think of the fringe as a list in Python, we can make sure that extending it this way, they will sort of be, put behind the elements that are currently in the fringe. So whatever we first put into the fringe will be popped out before something we later put into the fringe later on. Here is an example. So say the fringe would contain the elements 1, 2, 3, 4. This is basically the situation where we have expanded and not. Now the fringe would contain, well, I go back to show it to you. So this is the fringe now, and 1 and 2 and 3 and 4. And we select an element from the fringe, we sort of pop it, the node will be 1, right? And the fringe will not contain that node anymore using the function pop. And then we extend the fringe by just concatenating the successors of node 1. And so we will end up with the list of 2, 3, 4, 5, 6, 7. And if we pop the next element, this will be 2, so it's still a node from level L. And we have to pop all these nodes from level L before we reach the nodes from level L plus 1. So this is if you ever are faced with having to do it yourself, then here you go. FIFO-Q. Now, your question with the brute force. Yes, this is brute force. So we have to think about the complexity of this and what kind of guarantees we can expect if we expand state spaces using DepthFirst Search. First of all, if the branching factor, so if there's just a finite number, branching factor is finite number of possible successor states. Sometimes that could be infinite. I can't think of a situation like that right now, but if it is finite, there's only finitely many possible next actions leading us to possible next states, then DepthFirst Search is complete. That is, it will find solution. It will find a solution. If the solution, the node or one of the nodes that contain a solution reside on level D of the tree, it will be found once we have uncovered the levels 0 to D minus 1. It will find a solution. Cannot miss them, so it's complete. But as you said, this solution does not have to be optimal. There's no guarantee for us that the solution would be optimal. When we discussed the issue of how to define these cost functions, these step costs, I said we don't worry about that. But one thing I can tell you is if we have a cost function that is monotonic with the number of steps it takes to reach that state from the initial state. Right? If it is obvious that every solution on level L plus 1 incurs higher costs than a possible solution on level L. If it's more expensive to take yet another step than to take, say, L steps, it's more expensive to take L plus 1 steps. If we have this guarantee about our costs, then we can indeed rest assured that DepthFirst Search is also optimal. But this highly depends on how we choose the cost function. But if it is monotonic with the layers or levels of the tree we expand, we are good.
But only the levels of tree is enough, because in one level you can have different costs.
Sure.
So
But
only the levels is not enough.
Yeah, it's not enough, but it has to be a function of the level of the tree.
I mean, not only the function of the level of tree, also the order in one level.
Yeah.
Say in one level we have, I don't know.
Yeah.
3, 1, 4.
Sure.
In this case, we have 1, 3,
But if you choose, okay, yes, if you choose the function such that it is at least monotonic with the depth of the tree and some other tricks, you can ensure optimality. I mean, you can do that. You can do that. Right. But in general, it is not optimal. And again, why am I sort of hand-waving these details? this is just tree search, and it's not really, you know, our main focus in this lecture. If this was a hardcore AI lecture, where we would do nothing than AI techniques, then we would go through all these details. But basically, we have to discuss this, because this is where computational intelligence for games comes from. But in 2 weeks from now, we'll totally switch to machine learning, and there is no AI anymore. All right? So this is why we have to look into this, but not at that level of detail. Okay? I am sorry about that. Complexity is order of b raised to the d plus 1, where d is the level on which we find a solution. Why is that? Look at this tree, and let us assume that the solution we are actually interested in is the last node of level, is in the last node of level d. But as we are doing breadth-first search, so we expand these two nodes, and then we go to the next level, and we have to expand all the other nodes before we indeed examine this node. This is you know, we expand the node, we add. So when we add this node to the fringe, we have not examined it yet. Right? So it is in the fringe, but before we examine it, we'll actually have to examine all the successors of the nodes that are already, like that are predecessors in the fringe. So, and in that sense, yeah, well, we have to expand basically all the nodes in level d plus 1 minus the b successors of the node we are interested in. But this is, you know, b raised to the power of d plus 1 minus b. This is basically of the order of b raised to the power of d plus 1. This is not really expensive, but for the example we have seen, that was really bad, because the solution was here and we had to do quite some examination until we finally found it. And that is to say that even for moderate choices or moderate values of b, whatever problem we are dealing with, if this branching factor is not really very, very small, then this naive breadth-first search is infeasible in practice. The problem is not so much runtime, because in the end we just have to look at d plus 1 levels, and if there are m levels, that could be much, much worse. But we have to keep all the nodes that have already been expanded somehow in memory to examine them further on. Right? So this basically incurs memory problems. Now, then, what about depth-first search? This stuff we have already looked in when we discussed min-max and alpha-beta pooling. Now, you all know this, that in depth-first searches we can cast this idea as basically always to first expand the deepest node in the current fringe. Right? And if we, by doing that, would reach a terminal state, a node from where there is no possible continuation of our search, well, then we would have to go back one level up the tree and expand the next successor and see what happens. So here is depth-first search for our problem, for this, this didactic illustration where we want to find this solution. It proceeds like that. Deepest level in the fringe is n naught. From there we expand one of its successors, which is now the deepest node in the fringe. Note that n naught is still in the fringe. It is a leaf, because even though it has a successor, and this technically is not a real leaf, but it still has unexplored successors. And in that sense, it's still in the fringe, and I said everything that is in the fringe is a leaf. It's not a true leaf, but let's pretend it was. N1 is the deepest node in the fringe right now. We expand it further. We find a node N5, which is now the deepest node in the fringe. We expand it further, find N13, which is the deepest node in the fringe, but cannot be expanded further, so it's put into the closed list. we have to go back one level up in our recursion. From there, we go down again, find N14, again something we cannot expand further, move it to the close list, go back up, find N15. Now we have expanded node N5 to the fullest, we can put it into the close list. All of a sudden the deepest node in the fringe is N1 again. This is now, if there's no successors, all these things have been fully, no unexplored successors, they have been fully expanded and examined, they are in the close list. These two are still in the fringe. The deeper one is this one, so we have to continue with N1. We do that, find N6, which we have to expand, and we have found the solution. This is a lucky coincidence, right? In this example, actually depth first search was more efficient than breadth first search. We had to look at way fewer nodes to find that solution. In general, that does not have to be the case. Indeed, before we talk about this, again, some implementation trick. We could, in the case of depth first searches, implement the fringe as a last in, first out, or LIFO queue, also called a stack. Let's see at how Python would do this. Again, we are given the fringe, which we realize as a list in Python. We pop the first element and call that node. And now we have this last in, first out. This is basically switching the order of how we append stuff to one another. Right? While for the first in, first out, we had fringe plus successors. Now we have successors plus fringe. That's it. That's it. Here is an example. So say if the fringe was 1, 2, 3, 4, we pop the first one, we get new fringe 2, 3, and 4, and 1 is the node we are now going to expand. And if we append the fringe to the successors of the node we are going to expand, then we have 5, 6, 7 before 2, 3, and 4. Right? And therefore, if we now continue popping from the fringe, we'll first get the successors of node 1 before we actually continue with the successors that are already in the fringe. There you have it, last in, first out queue. Depth first search is incomplete if the search can continue forever. That can happen. There are, we can formulate problems where we can, continue expanding these search trees for all eternity. Right? Because from every state we are in, we might, come to another successor state that is not yet in the closed list, but sort of very similar to something we have done previously. That depends on the problem. If the problem is such that in principle we could continue searching forever, then depth first search will search forever in all likelihood. Yeah?
In the previous example, is it related to the tree that...
No, not at all. No. These are, all the examples I'm showing you here are very silly, and I'm just showing them. And of course, by showing them to you, I want to provoke your brains. Right? Because, my job is to tell you stories like these, and your job is to work with them. And so, no, that example was not related. So his question was, if that example was related to the tree, we just thought, no, it is not. It is not. It's just illustrating the idea of a last in, first out queue or stack. I talked about this in the very, very first lecture. So, seriously, your job is to take these things and begin crunching them. Well, that is what learning is all about. Actually, if I do mistakes, it's even better for you, because why did you say? And then you start, thinking about these things, and indeed find, oh, there was a mistake, and indeed it must be so, and then you have learned something. So it's actually, it's good if I present examples that have nothing to do with the talking about earlier. Great. Depth first search is also not optimal. It may return a solution found in the wrong subtree, say. And if it has found something, then it has found something, and it will not backtrack until it found something better. It's not what we can do about it. and memory complexity of depth-first search is just b times n. This is great because we do not have to keep track of all the nodes in a level, but basically of all the nodes in one branch, and that's usually less. Well, if that m is large, then this is very bad. But the bad thing about depth-first search is the time complexity, which is b to the m. And this is because, if you think of it, again, say the solution you're looking for is in the very last node of a certain level. Let's call that level D. Then this is the worst thing that can happen, right? In order to examine that node, we basically have to examine the complete tree, which is to say we have to look at this node, b to the 0 is just the root node, then b to the 1 is the number of successors of the root, and so on and so forth. We have to add this all up. This is this sum. That sum here would be the complete number of nodes in the tree, but we have to subtract the number of nodes in this subtree. Right? So you can think of the worst case complexity of this as having to expand the full tree, which would mean we have to examine this many nodes, but not having to examine this little subtree there, which means not actually having to examine this many nodes. But if we subtract this sum from this sum, the result is totally dominated by this term. Right. And therefore, all of this is of complexity O of b raised to the m in a worst case. This is not at all feasible in practice. And not so much because we would have to keep track of many nodes as we have to do with breadth-first search, but because of the computation time this incurs. It's not really feasible for most practical situations. Yeah, and then there are many, many variants of this. For instance, I mean, if we said there is something like a cost function, we can include that in our search strategy. The two things we have looked at right now are purely mechanical. This is not using any side information whatsoever. We just say, okay, we always go for the deepest node in the tree, or we expand the shallowest nodes in the tree we have looked at so far. But this is plainly mechanical selection of nodes for subsequent examination. Right. Now, we could include costs we have computed for path until a certain node, and then expand that node of the lowest path cost, and we will discuss that next week. If, however, all the costs for a path are equal, for instance, in a graph, all the edges may just carry a weight of 1. If there's no additional information available, then we can talk about this situation as a graph where the edges are labeled with a weight of 1. Then this uniform cost search becomes breadth-first search. We already talked about the idea of depth-limited search. And that, if you remember, was not expand the tree to its fullest, but like given the initial state, just go down a number L of levels, which is bounded by some upper bound lambda. And then if this lambda is indeed infinity, depth-limited search becomes depth-first search. However, if it is less than infinity, we can avoid problems of, as we just talked about, infinite many expansions, depending on what kind of problem we're talking about. So probably is a good idea to set a bound lambda for the number of levels to explore anyway, because otherwise, depending on the problem, this algorithm may never terminate. Yeah, and if that lambda is chosen less than, say, the level on which the solution we are after resides on, we'll never find it. It's incomplete and it's guaranteed to be incomplete. So therefore there is this idea of iterative deepening depth-first search, which is somehow depth-limited search in lots of iterations where we gradually increase the depth we are considering for, the maximum depth we are considering for expansion. This is thought to combine benefits of breadth-first and depth-first search, and generally seen as the best uninformed search strategy when both these parameters, b, the branching factor, and m, the number of, or the maximum depth of the tree, are large, and in particular when we don't know on which level d the solution resides, then this is considered to be the best uninformed search strategy. Yeah, and then there's this idea of bidirectional search, which basically says, well, we can probably find the solution in terms of two tree expansion processes. Namely, we could search forward from the initial state and backward from the goal state. What does that mean? So, for the problem of traveling from Bonn to Bremen, for instance, I could expand this node and that node. I basically have two fringes. Let's do that. I expand the Bonn fringe, and everything in the Bonn fringe is sort of red, and everything in the Bremen fringe is green. And yeah, if we say we're to expand this Bremen node like in a totally uninformed manner, we of course would find Hamburg and Hanover, but also Osnabrück. Now, this node cannot be expanded further. These two can. That would lead us to examine these nodes. Cologne can, of course, be further expanded. Let's see what happens. So yeah, we do this. We have expanded this tree further, getting these two nodes, this one getting these two nodes. We continue. And now we end up in a situation after a couple of steps where these two searches intersect. This is great, because now we have found a solution. We just have to sort of backtrack. How did we reach this from there, and how did we reach this from here? Put it together, and there we go. This is extremely efficient, and this is how you should do it, but of course it only works if we know the goal state. So it doesn't work for tic-tac-toe or chess, because there we just want to win, no matter how. We want to reach one state that, you know, corresponds to a win. In path planning, we have a single previously known, clearly specified goal state, Bremen. Our initial state is Bonn. We want to find Bremen, so therefore we can start a backward search from Bremen. And indeed, all the path planning or route planning devices you have in your cars and on your smartphones, they use these bidirectional searches. Because otherwise, it's too expensive. So if you enter your destination and the device knows where you are, it starts two searches which eventually will intersect. And once they intersect, you have found a path. And to wrap this up, so I already said it, and I'm sorry about it. We have to look into these things. It is good to remember what we maybe learned a couple of years ago, but these things are not our main focus. And once we're done with this, we'll actually do some more, I'd say, interesting stuff, because pattern recognition and machine learning. So, but if you are interested in all the dirty details, I would like to refer you to the book by Russell and Norwick. They have an extended chapter on uninformed search strategies, and lots and lots and lots of details. Right? I'll mostly ignore this, because after all, this is just uninformed search, and nobody in their right mind in the year 2014 would tackle a problem using uninformed search anymore. All right? But this is basic knowledge, so now we're done with that. Good. Yeah, okay, so to prepare ourselves for things to come, what else could we think of? All right. We've seen there's this idea of uninformed search and informed search. Maybe there's something in the middle, right? And yes, probably there is. So what about if we were to expand this search tree in a random manner? Our strategy would not be so mechanical as to just always choose the deepest node in the fringe or always choose the shallowest node, but you know, purely just pick some node from the fringe. Let's see what happens. In this, again, contrived example, from the root node N0, we first expand N4. Then, again, we pick some node in the fringe, which at this point contains 2 nodes. It so happens that it is again N0 that has been chosen. Now, this fringe contains 3 nodes because for N0 there are still 2 possibilities for further expansions, and even though it's not a leaf in the classical sense, it's a leaf in the fringe. We pick N2. From there, next thing to expand is indeed N1, leading to N6, and then randomly, it really I had to run it a couple of times, but after a couple of times, it found the solution in just a few expansions. Right. So this is it has found the solution. It has found the solution. If the branching factor is small and the maximum depth is small, this works really well. Surprisingly well. Right? Can go horribly wrong if the branching factor is large and the depth is large. Then this may really, it eventually will find the solution.
Can traverse whole tree.
Pardon?
It can traverse whole tree.
Yeah. In the very worst case, this can, consider every node in the tree until it finally. So this is not a good idea. This is really not a good idea. However, it suggests 2 possible ways where we could take it from here. And the first one is called Monte Carlo tree search. And that is a surprisingly recent development, which is a random tree search algorithm, but not so stupidly random as what I just showed you. This random tree search algorithm, Monte Carlo tree search, makes use of information that has been systematically gathered over many random expansions. And this, in the year 2014, is the method of choice. And we'll study that in the next lecture. And then, coming back to informed searches, right? What happened there, like this expanding N0 to N4, then to N1, then to N2, then to N6, and then to N16. This could also be the outcome of a search procedure where we had used additional information. Right? So if for whatever reason in node N4 we would have known, okay, this is a state of a certain value with respect to our goal, and 2 is a state of a certain value, and 1 is a state, and we could rank them and then find that N1 is actually right now the best one to expand, and then from there we'd find N6, which then would rank highest in the fringe, and from there we'd find N16, which is like the outcome of, or the goal of our search. So if we had an informed search process, which again requires a way of ranking the nodes so that we can pick the best one for further expansion, then the final search tree would look like this as well. Right? So these are the 2 things we are going to study next time. That is, we'll spend a lecture on Monte Carlo tree search because you really need to know about this one. This will maybe, I don't know, be dramatically more complicated than what we have seen so far. And I wanted to point out that on the website I have uploaded a set of slides on basic terms and ideas, probability theory and statistics. And if you feel that you are not really comfortable with probability and statistics, you should have a look at those. Because that will come in tremendously handy next time when we study Monte Carlo tree search. Right? And yeah, I've been thinking about it also if you would say that even by looking at the slides which I uploaded to the website, you still are not so comfortable with probability theory and statistics, then you should tell me. Because then I will insert a lecture on probability and statistics. Because in 2 weeks from now, everything will be probability and statistics. Right? And we'll see it in the context of tree search next time. Then, however, before we continue with these like more learning approaches to game AI, we'll have a final look at tree search techniques, in particular at informed search techniques. So that is an outlook for things that are to come. And to summarize what we did today, a surprisingly simple thing, yet very important thing, was that we studied the notion of a well-defined problem. We now know what constitutes a well-defined problem. These 4 ingredients: initial state, successor function, goal test, and so on and so forth, path cost. We saw that this idea of tree search, which up until today we basically considered as an approach to deterministic, turn-based, 2-player, zero-sum games of perfect information, can be applied to a wide variety of problems, if, that is, the problem can be cast in terms of a discrete, or the problem we are dealing with can be represented in terms of a discrete state space where there are well-defined transitions between discrete states. Then we can try to reach a goal state, starting an initial state, using tree searches. Yeah, important concepts: optimal solution, fringes, search strategies. We looked into a couple of search strategies. In particular, we had a look at common, classical, uninformed search algorithms, in particular their characteristics, strengths and weaknesses in terms of runtime complexity, memory complexity, and so on and so forth. Are there any questions? Great. Okay, then we see each other again on Monday. Thank you.